The very first thing that I'll ever measure on a soil sample, that any laboratory will measure on a soil sample when it comes in, is the soil texture. And the word texture creates a mind's eye picture, doesn't it? What's the mind's eye picture that that word brings to you? Yeah, the way it feels, right? Texture is kind of that sensory kind of word there. And early on in the birthing stages, I guess you might say, of soil science, that's the way we measured it. It really refers to the proportion of the sand, silt, and clay-sized particles in the mineral fraction of the soil. But each one of those sized particles imparts a different feel to the mass. Sands are very much bigger than silts, which are very much bigger than clays. So they're a size fraction. And our fingers have enough resolution to detect even the very smallest sand particles. We can feel the grittiness of the sand between our fingers if we take a soil sample, wet it up, and rub it between our fingers. Silts are so much smaller that we can't detect the individual particles with our fingers, but that means that they're smooth to us when we rub them between our fingers. But when we pull our fingers apart, it's not sticky with silt. Clays are so much smaller, and because of some of their character that we'll talk about here in a minute, they're not only smooth because we can't feel the individual particles, but as we pull our fingers apart, we'll feel the stickiness that's imparted by clay. And we can actually train ourselves to know what the predominance of any one of those feels is of a soil sample, and we can begin to classify soils by texture that way. And that's the way it was done early on. More and more, scientifically, we can actually measure directly the particle content itself of the different things, and we'll talk about that here as we go along. But there's a couple of things I want you to know about these particles besides their grittiness or their not grittiness or their size. Sands and silts are typically very round, spheroidal, we call it in nature. They may be a little bit blocky and have some facets on their edges, but for the most part they're rounded, and they are just smaller and smaller chips off the original block. They are smaller and smaller pieces of the original parent material from which they were derived. And so we'll find the very same minerals in the sand and silt fraction that we would have found in the original parent material that soil came from. So let's say it's granite, for instance. What are the minerals in granite? We find a lot of quartz in the sand and silt fraction. We'd find a lot of feldspar in the sand and silt fraction. We'd find to smaller extents things like magnetite, hematite, and hornblende, which are those dark black flecks that you see in a granite rock that would show up in the mineral content of the sand and silt fraction. Clays are not just a size fraction, but they're an entirely new class of minerals. We call them secondary minerals. These particular minerals developed in soils in place over time as the stuff that was dissolved out of the sand and silt and parent rock recombined in the soil solution to form new mineral crystals. And you've heard the names of some of these in the past, things like illite and bentonite and kaolinite and montmorillonite, but you may not have known that those were clay minerals that developed in soils in place over time at the surface of the earth. How many of you ever had a spoonful of kaopectate when you were a kid to calm your troubled stomach? Well, all that was a spoonful of suspended kaolinite clay in a bubblegum flavored water, okay? That's really what it was. And it has some absorptive qualities for things like the acids and thing in your stomach to kind of calm it. It's kind of an interesting.
I just kind of missed part of what you said. So it's basically all the minerals broken down to a point where they can start.
Yeah, they dissolve into the soil solution, and then those materials recombine into new mineral crystals. Yeah.
Okay, thank you.
And depending on, how many layers are in each one of those crystals and things, then they take on different names. Okay, but we're not going to go to that extent. There's a great class that you can take at the university, clay mineralogy, but it's a fairly exacting course. I've taken that. It's very interesting. Okay, but Let's take a look then at the difference in the clay mineral particles compared to the sands and the silts. Because they recombine into new crystals, they are literally a little flake of a new crystal that forms in the soil, which is much broader across than it is thick. And it's hexagonal in its perfect condition. In nature, we don't find a lot of that because they're broken and chipped and things like that. But that would be its perfect configuration. And these are really, really small, tiny, tiny little flakes of these crystals that develop in the soil. We said that they develop in place in soils over time, and so they develop in fairly widely changing environments while they're trying to form. I mean, there's big fluctuations in temperature, there may be big fluctuations in water content, maybe not all the things that it needs to form will be found at any given time. And so as these crystals begin to form in the soils, sometimes there's perturbances that cause them to be imperfect in their structure. Let's go back to basic high school chemistry, and don't start panicking. What's the chemical structure of water? You can turn it on, Mike, if you want. H2O. Remember from basic high school chemistry, any molecule, any compound that we find in nature wants to be stable, right? It wants to be electrically balanced. And is that the case with water? Well, yeah. We've got 2 negative charges from the oxygen and 2 individual positive charges from the 2 hydrogens. We're balanced. We're happy that's a stable molecule compound. Well, we could draw out the structure of an aluminosilicate clay, and it's huge, okay? But it has all of these different things in it, and it tries to be balanced as well. But what happens is, because it is developing in this imperfect environment, that sometimes things go amiss in the structure. And typically that's a positively charged ion in the structure. If I don't have a positively charged piece of the puzzle, what am I left with? I'm left with unsatisfied negative charge. So if I were to say, let's take one of the hydrogens out of here and I create what we call hydroxyl, it would be negatively charged. And the same thing happens with our clay minerals. As they form and miss things in the lattice of the crystal, we end up with negative charge on the surface of the particle that's unsatisfied by the missing pieces within the structure. But that's really important to the function of clays in the natural environment, because then they become a magnet board. And all of the things that are positively charged that are floating around in the soil water, things like magnesium and calcium and iron and molybdenum and zinc and copper, which happen to be nutrient elements that are positively charged, can stick to the surface of the clay like little refrigerator magnets, retained there for later use by plants and animals in the system. And so this negative charge on the clay particle is really important to the function of the soil. And it's really important that we have clay in our soils. People try to avoid having clay, but clay is a really good thing to a point. We can get too much of a good thing, okay, in this case. Sands and silts, remember, they're the original minerals that were in the rock. And they formed most likely in the magma mass as it cooled originally. And as it did in a fairly controlled environment, and all the stuff that was there that was needed was in the big magma soup, and it formed fairly perfect crystals. So there's very, very little charge on a sand or a silt clay or a silt particle, where there's a lot on the clay. And so it's important that we have some of that in there to help with the at least nutrient retention in this case that we've talked about. Now let's turn our attention back to water over here for a minute. Water, we said, is electrically balanced. But if we look at the shape of the water molecule, we get a big oxygen atom and 2 little hydrogen atoms that sit on top of it like Mickey Mouse ears. And if we draw a line through the oxygen atom, we notice that the hydrogen atoms tend to stay on one side of the molecule and never really visit the other side. It's kind of like a neighborhood, okay? This is where all the nice houses are over here and not so nice on this. And so we get a little positive neighborhood on this side where the positive charges hang out. And a small negative side of the molecule over here where they don't visit very often. So what happens when that happens? We get what we call a dipole that develops on water. Have you heard that water is a universal solvent, right? You've heard that phrase probably. The only way that water could ever dissolve anything is the fact that it has this character. Because those little charges can just lightly tug on solid materials and weaken the bonds between the other elements within the solid and slowly pull them apart till they eventually dissolve into the water itself. Okay? Water wouldn't have that ability if it didn't have this partial charge on either side. But because it has that, it can also stick to the surface of the clay and be held there like a little refrigerator magnet and retained for later use by plants and animals in the system. So this charge character of the clay particle has a lot to do with water retention as well, and nutrient retention. You guys already intuitively know that, right? If you put water on a sand, what happens? It goes right on through, partly because it's got really big pathways to flow through. But it's mostly because the sand doesn't have any charge on it, and it can't hold on to the film of water on its surface like the clay can. So that's a pretty interesting thing. Why do you wax your car after you wash it? Not because you can buff that wax up to a really bright shine, which is part of it, but wax has almost no charge at all. It's a fairly charge-less material. Your metal surface of the car is very highly charged. It's got a lot of charge in it. So what we're trying to do is hide that charge so it doesn't attract the water. We don't want the water coming down and sticking to the surface of an unprotected metal because it's going to leave things that are dissolved in the water behind, the little water spot on there, or even in the extreme corroding that metal over time. So we put the wax on there so that it hits a non-charged surface and doesn't have anywhere to stick, and it rolls right on off, right? And doesn't stick to the surface of the car anymore. That's why we do that. It's physical chemistry. You didn't know you were playing with physical chemistry when you did that, okay? But that's a really important characteristic that's also imparted by clays in terms of water retention. So let's take a look at, you can turn it off now, Mike. We're not going to do any more board for a bit. Let's look at some special cases. Sodium, Na, is a single charged positive ion in soil solutions. If it sticks in abundance to the surface of a clay particle, it's got a really big radius. And when it gets in between the clay particles, it tends to push them apart. And it gets them so far apart that they really don't interact with each other. They're just kind of out there surrounded by sodium all by themselves. Okay? Yeah. In that case, we call that system dispersed, because the clays are all kind of pushed apart and they're all there in the soil mass, but they're really not playing together. They're just kind of there by themselves. Contrast that with if we had calcium in between the clay particles there. Calcium is divalent, has two positive charges and a much smaller radius, and the clay particles can come into closer contact with each other and are bridged by the calcium that's there. And so they kind of play together as a group. We call that system flocculated. Well, why do we care about that? What's that?
It's like rock.
Well, no, this isn't compacted. These aren't that close together, okay? That's a little bit different, but that's kind of going that direction. But I'll show you why we would rather have a flocculated condition than a dispersed condition, okay? Here's a really good example of why. Here's an electron micrograph of a flocculated clay and a dispersed clay. You've all played with this idea of flocculation when it came to playing with Legos, either as a kid yourself, they've been around that long in many cases, or with a son or daughter or a grandchild or niece or nephew or whatever. And there's something interesting when you play, particularly with the Duplo blocks, and you make a big tower. It gets to a certain point where the genetic freak out of a 3-year-old will not allow it to get any higher, right? So they have to knock that tower down. When they knock it down, does it break apart in individual blocks, or do they kind of stay together in groups and tumble in on top of each other? They do. They have this, something's holding a few of them together, but then the energy that goes into them breaks them apart, but they tumble in on top of each other as groups of blocks. And that's what happens in a flocculated system. We've got right here a big Lego tower stack of individual clay particles, one on top of another, big pancake stack. And it gets to a certain height or length, and it can no longer tolerate being in this big tower, so it breaks apart and tumbles in on top of the rest of the pieces. And the flocks themselves, when they tumble in on top of each other, leave fairly large pores in between the flocks, which allows for air and water to move through that system pretty readily, and can then get in between these clay particles and be stuck to the surfaces of the clay and then retained in there as well. So we have good exchange, and we can take advantage of the properties of retention that we talked about before. Okay? You can see that, you know, these aren't all perfect in that hexagonal structure that we talked about before. They're chipped and broken and everything else. So we don't see a lot of perfect crystals in here. A dispersed condition, when they're all hanging out by themselves and we put a little energy into it, say we fluff up the soil or we bust in with a bunch of water and we mix it all up and we float it up and it all starts to settle back down. If they're not acting together in groups, they're going to start to orient all in the same direction. And they're going to overlap edge to edge, and they're going to form sheets as they settle perpendicular to gravity. What you're going to end up with are these sheets upon sheets upon sheets of oriented clay particles that form crusts at the soil surface, or they form these coatings that then will lay over the openings of pores at the soil surface and block that pore from being able to communicate air and water into and out of the soil. These get thick enough, and it's really hard for a water molecule to get up here and make its way through all of those layers. It might make it through one and encounter another and encounter another, and so the water infiltration rates go way, way down in a crusted condition. A seed that's germinating underneath one of these may find it really, really difficult to push up through it and get to the surface. A root, if this is down below the soil surface where it happens, a root's going to have a really hard time penetrating through those crusts that might form. So we'd rather have a flocculated condition than a dispersed condition when it comes to the clays. And that'll become important later on when we talk about affecting and manipulating some of these properties. So soil texture is the very first thing I'm ever going to measure on a soil, because intuitively you guys already have a feel for the fact that you can kind of predict at least ranges of properties that a soil might have as we go from a coarse textured sandy soil to a finer textured clay soil. Things like compaction potential. It's going to go up if we have more clay, potentially. Drainage is going to be less in a higher clay soil just because it's harder to get water into and out of the system. Aeration, the same thing. Available water is a little bit interesting because available water is the water that's stored in soils that can actually be extracted by the plant. And that goes up as we get increasing amounts of clay to a point. And then we get to that point where we get too much of a good thing. We get to a point where we have so much clay in the system that the properties of the clay for water retention take over. And it holds more water with more clay content, but it holds on to it more tightly than it does at lower clay contents. And we actually get a reduction in the amount of water the plant can extract at higher clay contents. So you already have kind of an intuition as to the physical properties of a soil. So there's ways of measuring soil texture. We already talked about by feel a little bit. If you Google soil texture by feel, you'll get a couple of hits on some yes-no decision algorithms that you can say, okay, I take a ball of soil and I wet it up and I squeeze it in my hand and I rub it between my fingers and I make a snake and a ribbon and those kinds of things. And depending on the yes-no questions that you answer as you do those things, you can get yourself down into a soil texture category by doing that. I had a professor, I tell the story of all these classes, of the professor I had at Utah State as an undergrad way back that used to go out with us on field trips, and he would grab a chunk of the soil and throw it in his mouth and wet it up and stick it to the roof of his mouth and rub it between his teeth to feel the grit and things like that. And he could tell you within a couple of percent what the sand, silt, and clay content was of that soil. But remember how many critters I told you were holding in your hand? Maybe not the best thing to do. He is still alive, which is a good thing. The more sterile or antiseptic way of doing it is to take a soil sample and send it to us, and we'll tell you what the sand, silt, and clay percentage is on a soil test. But you can do almost the same thing with a fair amount of accuracy, reasonable accuracy to at least do a soil texture analysis with this simple jar method. And you know, when they gave us more time to do these classes, we'd actually do this in class, but we don't have a chance to do that. But I'll describe it for you. And the details of it are in chapter 3 of your Master Gardener manual, okay? I put all the times and calculations and things in there. But get yourself a straight-sided jar. Mason jars work okay. I use a Prego or Ragu spaghetti sauce jar because they're straighter. And what we're going to do is we're going to be measuring depths of layers in a jar. So I don't want any curvature of the jar that's going to confuse that depth measurement. So don't use a mayonnaise jar. They're awful. They're really rounded at the bottom. And you're going to take that jar and you're going to put some dry soil in the bottom of it. Crush this soil up. Go out and take a sample in your garden or whatever that you're interested in doing this with. Crush it up, and I don't know how many of you have got a Rubbermaid or Tupperware colander, or even a metal colander with the little holes in the bottom, the little square holes in the bottom. That's about the size of the biggest sand particle. So if you run it through the colander, you'll basically sieve your soil down and get the sand, silt, and clay fractions. The rest of the stuff, like the debris that's in it, you can just toss out, okay? Or the rock and stuff like that. Put that down in the bottom of your jar and tamp it down so it settles real good. There's not a lot of airspace in there that's beyond the normal in your soil. And then I want you, before you do anything else, to measure that depth. And 1.5, 2 inches of soil on the bottom. This says fill it up a quarter full. That's overkill. Maybe 1.5 inches, 2 inches in the bottom of the jar. I want you to measure that depth. That's your initial depth of soil that you put into that jar. Then I want you to put a fair amount of water in the jar. Fill it mostly full. Leave some air space so you can shake things up on there. But use distilled water. Why distilled water and not tap water or raw water? Yeah, we've got dissolved minerals in the tap water and the raw waters. This is the only time I want you to have a dispersed system, okay, in this jar. Not out in the nature, but in this jar. I want it to be dispersed. I want all the particles to be just kind of hanging out on their own and settling with respect to gravity as it has a chance to work on it. So I put the water in, yes.
So, I'm sorry, I missed the part with the colander. You said to screen it?
Yeah, just bust it all up and just sieve it through the colander, and that'll give you the sand, silt, and clay. Okay? Yeah. Thank you. Shake it up. And make sure all of the little aggregates and chunks and clods and things are broken up in there, and they're individual particles as best you can get. And then stop shaking and start timing. What's going to happen if I stop shaking? Things are going to start to settle. What's going to settle first? The sand. It's the most massive particles. It's going to start to settle. In your book, it'll tell you after 40 seconds, all the sand-sized particles have settled to the bottom of the jar. We know that from physics. Don't ask me to explain it. It's too involved. Darcy, or not Darcy's, but Stokes' law of settling and all that kind of stuff talks about the math. Anyway, okay. So the sand's going to settle out first, 40 seconds. Make a mark at the top of the layer that forms. Why don't you just measure it? Well, it's because settling's not going to wait for you to take a measurement. It's going to continue. What's going to settle out next? The silt. It's the next largest particle, the next most massive particle. So it's going to start settling out right away. So make a mark at 40 seconds, and then you can go back and measure it, because the silt's going to continue to settle on top of that. And after 2 hours, all of the silt has settled out. So you can make another mark at the top of the layer. And now you have 2 additional depth measurements. The sand layer that's from the bottom up to that first mark, and then just that little increment of depth that's accumulated from the silt that settles above the sand. Not the whole depth, but just that little increment of depth, which is your thickness of your silt layer. So then I've got 3 things after 2 hours, and I can do some math. I've got the initial depth. That's what you put in before you put anything else in the jar. that you measured. Then I've got the depth of the sand after 40 seconds. And then I've got that little increment of depth, which is the silt depth after 2 hours sitting on top of the sand. Then I can do some pretty simple math. The depth of the sand divided by the depth that I had initially in the jar. Multiply that by 100. That gives me my percent sand. It's just a proportion of the sand of the overall mass of soil that you had times 100 gives you the percent sand. So then we do the same thing with that silt layer. The depth of the silt divided by the initial depth, all times 100, is equal to my percent silt. So after 2 hours, I can calculate those things, and I have then 2 things out of 3 that sum up to 100%. Do I care if the clay settles? I don't. I can get the clay by difference, right? Add these 2 up, subtract it from 100, that's my clay percentage. And it's a really good thing that I don't have to wait for the clay to settle, because it may take 100 years for that to happen. The clay particles in some cases are so tiny that the random motion of the water molecules continues to resuspend them in the water. So I don't have to worry about the clay. So you then can go with that information, and that's a little bit what it looked like. You wouldn't see a clay layer like this thing shows in your notes, because we've added something to flocculate all the clay and settle it out so that we can see all 3 layers. But you'll just have a sand and maybe a silt layer, maybe not, depending on whether there's any silt in that soil or not. And then you can go to what we call a soil textural triangle. If you Google soil textural triangle, you'll get hundreds of hits on these things, of these pictures, these graphs. They all have something in common. They're triangular in shape, and they have sand percentage on one leg, clay percentage on another, and silt percentage on another, going from 0 to 100%. So for purposes of demonstration, I chose one that had 60% sand and 10% silt. After these calculations, you see these arrows. It tells you what direction to read those different separates on. So I come up the 60% line for sand. I come down the 10% line for silt. They intersect, and by difference that leaves me 30% clay, and hopefully that adds up. Yeah, 60, 70, 30, 10, 100. Okay, perfect. That intersection point puts me smack dab in the middle of this category called sandy clay loam. Great, I've named it. So what? So what? Well, we soil scientists, we have odd ways of spending our time. And we've played around with these soils for a really long time. And we know that the soils within that named category have very similar properties. They have very similar ranges in infiltration rate and water retention capacity and compaction potential and all kinds of other properties that I can then go to a table of and find out what ranges of properties I'm going to expect to have to deal with on that particular soil in my yard or wherever it comes from, which is really nice. Even with soil texture alone, I can get a lot of information just that way. Now, it'd be nice if we all lived in Loamville, where we have kind of the optimum distribution of the different sized particles. We have big particles from sand and little particles from the clays. We have big and small pores. We have unreactive and reactive surface area in the system. So we have a really nice mix of things. But the nice thing is that a lot of soils, in fact the bulk of soils, have loam in their name, which means they have loamy properties that are good to be able to use that particular kind of soil in a variety of different ways to grow plants and other things. Sometimes, however, we're out in the extremes here that we have to deal with, maybe manipulating those properties a little bit more to bring them toward a loamy character if we can. What has the most property on this real estate graph? Clay owns a big chunk up here in the corner. And that's that, too much of a good thing we talked about before. We get up above about up above about 40% clay, and everything acts like a clay regardless of how much sand or silt might be in it, because it just overwhelms the properties of the mix. Unfortunately, a lot of the folks that live out in the valley bottoms of our valleys in the state of Utah deal with upwards of 40% clay. So they're at the edge of this land of difficulty in manipulating the properties. Now, this kind of brings me to a question that people ask all the time. They say, well, if I've got one of these textural extremes, how come I just can't add clay to a sand or sand to a clay to improve the properties of that system? Let's take a look at why that's probably not going to work. Okay? It's very impractical and improbable for a couple of reasons. Let's take an acre of ground. It's the easiest thing to look at here. We're going to take 1 acre in area 1 foot deep. That slab or slice of soil, dry, based on the kinds of minerals we typically have in soils, weighs about 4 million pounds. So what's 1% of 4 million? 40,000, right? Drop a couple zeros off of it. 40,000 pounds or 20 tons. So 1% clay, for instance, in that particular soil weighs 20 tons, or 1% sand, or whatever it might be by weight, would be 20 tons of that material. Now, remember over here on the graph, I said all the soils within that category have very similar properties, right? So to change appreciably the properties of my soil, I have to get out of one category and into the next. Now, if I want to go from sandy clay loam up here to loam over here on the edge, we're talking about a 10, 15, 20% change in one of those soil separates, or 10, 15, 20 times 20 tons to make the difference. You better go buy a fleet of dump trucks. That's a lot of soil, okay? And so you might be a person of means that can actually afford it, and you might be able to find a supplier that can give you that much. But then you've got the problem of trying to mix it uniformly into the soil that you have, and you've increased the volume considerably of what you had already. And so changing the properties of a soil with a mineral amendment is pretty impractical. We don't recommend it. We never tell somebody to do it. What you're going to end up with are sand-coated clay clods. Or conversely, if you're adding sand to a clay, you're going to end up with cement, because what typically you'll buy is a fairly well-sorted sand mixed in with a calcareous clay, which has a lot of calcium carbonate in it. You're making concrete. Okay? That's all you're doing. So we try to stay away from mineral amendments to change the properties of soils. But remember, we said we had maybe 1 or 2% organic matter in our soil? That 1 or 2% organic matter accounts for about 40% of the properties in terms of nutrient retention and water retention and those kinds of things, which really affects the properties of the soil. So we'll talk about how important that little bit of organic material is and how we might manipulate that to our advantage in dealing with a textural extreme. So here's that discussion. If we have a problem soil, if we're out on one of these extremes of texture, if you have a sandy soil, at least you're lucky in the sense that you can get water into and out of that material, right? You have to water it frequently, and you have to use plants that are probably going to be able to tolerate drought, but at least you can get stuff into and out of and work that material. If you got too much clay, it's always an uphill battle. You may have so much clay that you may forget trying to do anything with it at all. and yeah, a raised bed or something like that where you can actually manipulate the properties a little bit more to your advantage. But regardless, even if I'm in too much sand or too much clay, the idea, universal to all soils, is to induce soil structure. So what do I mean by that?